So, welcome students for the chemistry lecture. And last time we have studied the general rules to study the three component system. All of you know the Gibbs phase rule. Here F it is equal to C minus P plus 2. Then this rule becomes for three component system F it is equal to 5 minus P. And if we consider a single phase present at a time, then F becomes 4. And it is not possible to draw a tetraquadral system. Okay. So, in case of three component systems, the we kept two variables here, pressure and temperature constant, and we use the reduced phase rule to study the three component system, and that phase rule is F it is equal to 3 minus P at constant pressure, and depending on this phase rule, when P it is equal to 1, we require two variables. When P it is equal to, that means phase is equal to 2, we require a 1 degree of freedom. And when the phases are 3, at that time that system is non-variant. Last time you have studied this. Then these are the certain rules to study the three component system. Here the scientists Cook and Bethlehem, they designed a equilateral triangle as a phase diagram of the three component system, and each of the corner or apex of a triangle represent 100% weight of one component. Suppose in general we have three components as A, B and C, and the three apex or apices of the triangle, they represent 100% of A, B and C respectively. The same apex will represent 0% of the other two components. Then the area within the triangle represents all possible combinations of A, B and C to give the three component system. And a line drawn through any apex to a point on the opposite side, then all systems are represented by points on such a line have a constant ratio of two components. In a short, the any side of the triangle, it represents the composition of two components, and any line drawn parallel to one side of triangle represent a tertiary system in which the proportion of the two components are different. Okay, then this is the phase diagram of three component system. Here at this apex we have 100% H2O. Here we have chloroform 100%, and here we have acetic acid. And this system is a three component system in which water and chloroform, these are partially miscible liquids. These are partially miscible liquids. And if we add acetic acid into water and chloroform partially miscible liquid, the miscibility of the two liquids increases. And in this dome shaped curve, in this dome shaped curve, there is a three component system, and above this we have a single homogeneous liquid here. Okay, then here the each side it is divided into 10 equal parts to represent the composition of the systems. And as already I have told you, this corner it has a 100% composition and 0% other two components. Okay, this is the phase diagram of three component systems. Then in detail we will study the phase diagram of acetic acid, chloroform and water. Acetic acid, chloroform and water. As already I have told you, the acetic acid and water, these are completely miscible with each other. Acetic acid and water, they are completely miscible with each other, while the CHCl3 and water, they are partially miscible. And in this partially miscible two liquids, if we add acetic acid, the miscibility of these two liquids, it increases. Okay, and this curve here, C to B, this is a tie line, and tie line, it shows the composition of water in chloroform, and here the chloroform in water. These two compositions are in equilibrium with each other. As we increase the temperature, the, the miscibility of the two immiscible liquids increases with increase in temperature, and at this point here D, the two liquids they becomes completely miscible. That means the chloroform water miscibility it increases by the addition of acetic acid, and at this D point there is a single layer, only one single homogeneous liquid which contains the CHCl3, H2O as well as acetic acid, and within this area we have two phases or two conjugate solutions of acetic acid in CHCl3 and water, and acetic acid in water and CHCl3. This is the explanation of the three component system. Okay, in this area, dome shaped area, there are two phases, and above this area we have only one single phase, and these lines are called as tie lines, and at this D point the two phases they becomes a single phase, and this point it is called as isothermal critical point. Isothermal critical point or the pilot point. Okay, D point it is a isothermal critical point or the pilot point. This is the explanation of three component system. Let us begin with the next chapter, and that chapter is here thermodynamics. All of you know the thermodynamics, it is the study of heat and other forms of energy, and this word it is derived by the scientists from the Greek word, and it means thermo means heat and dynamics means power. Okay, so in the second chapter here you have studied the in detail the study of free energy, and in that the Gibbs free energy and Helmholtz free energy you are going to study in detail. Then see, thermodynamics, it is the branch of science in which the study of quantitative relationship between heat and other forms of energies it is involved. And all of you know the thermodynamics it is based on four laws, and that four laws are first law, second law, third law, and zeroth law of thermodynamics. And all of you know zeroth law it is based on the equilibrium. That means there is a equilibrium in between the two thermal bodies. And first law it is based on the conservation of energy. Second law it gives the concept of entropy, and third law it gives the determination of absolute entropy. Then all of you are very well familiar with the basic concepts or basic terms that are often used in the study of thermodynamics, and that terms are energy it is the capacity to do work, then work it is the motion against an opposing force, and there are different types of works as mechanical work it is given by P it is equal to delta phi. Then electrical work and it is given by N EC into F, and all of you know EC it is the potential and F it is the Faraday constant. Then the next term that is the heat, and heat is one form of energy which transfer without transfer of mass from one body to another body, and it is expressed in terms of joules or kilojoules. Then the next point that is the enthalpy, and enthalpy mathematically it is given by H it is equal to U plus Pv, where U it is the internal energy, E it is the internal energy, and this Pv it is the product of pressure and volume. Enthalpy it is the heat content of the system or any body. Then the system it is any part on which we concentrate our attention for the study that particular part, and surrounding it is the region outside the system, and each system it has a boundary. Okay, and all of you know the system plus surrounding it becomes equal to universe. Then again, all of you know the types of systems that are studied in the thermodynamics. That systems are open system, closed system, isolated system. You have studied it. Then there are different types of processes, and that processes are cyclic process, reversible process, irreversible process. Then any state of the system it is fixed by fixing the variables of the system, and all of you know the variables of the system are pressure, temperature, composition, concentration, etc. Then there are two types of properties, intensive property and extensive properties. The properties of system is a measurable characteristic of a system that is in equilibrium, and properties are either intensive or extensive. And remember, intensive properties are independent of the amount of mass present in the system, and extensive properties they depends on the amount of mass present in the system. And intensive properties are temperature, pressure, and density. Remember well, The intensive properties, they do not dependent on the amount of mass present in the system, and that properties are temperature, pressure and density. And extensive properties, they varies with the amount of mass present in the system. For example, mass, volume, energy, enthalpy as well as entropy. All these properties are extensive properties. Then these are the thermodynamic variables, and state of system is defined by specifying the thermodynamic properties. Then all of you know the thermodynamic functions. Here internal energy, it is equal to dq minus dw. Entropy, yes, it is equal to given by dq divided by t. Enthalpy, it is equal to h plus pv. Gibbs free energy, it is equal to h minus ts, where t, it is the absolute temperature, and yes, it is the entropy. Helmholtz free energy, it is given by A, it is equal to E minus Ts. And in this chapter, our focus is on the Gibbs free energy and Helmholtz free energy. In this chapter, you are going to learn in a detail what is the Gibbs free energy and Helmholtz free energy. Then the state functions, that means they depends only on initial and final state. The absolute value of state functions, it cannot be determined, and the state functions are internal energy, enthalpy, Gibbs free energy, Helmholtz free energy, entropy, in addition to heat. Also, they are the heat and work. Sometimes they are also a state functions. Then the thermodynamic processes are adiabatic process, where no heat transfer takes place. That means Q remains constant. Isochoric process, here the volume remains constant. Isobaric process, in which the pressure remains constant, and isothermal process, in which the temperature remains constant. Then this is the state of equilibrium. Then here other forms of energies, that means mechanical energy, thermal energy, electrical energy, chemical energy. All these energies are different and distinct and interconvertible into each other. And these different types of energies, they are quantitatively studied with the heat in thermodynamics. Then the laws of thermodynamics, it is not meant for your study. So the spontaneous processes, remember that those processes which takes place on their own accord under a given set of conditions. All these processes are called as spontaneous processes, and non-spontaneous reactions are those which do not occur on their own accord under a given set of conditions. And remember that in thermodynamics, for a spontaneous process, the change in Gibbs free energy is negative. Okay? Change in free energy, it decreases. Okay, non-spontaneous processes do not occur on their own accord. These are the examples of spontaneous and non-spontaneous processes. Okay, we will study in detail the Gibbs free energy. Here, this Gibbs free energy in a standard state, it is denoted by delta G0. It is equal to delta H0 minus T delta S0, where G0, H0 and delta S0, these are the free energy in a standard state, enthalpy in a standard state, and entropy in a standard state. And this is the quite important equation in the study of Gibbs free energy. Okay. Then in detail we will study the Gibbs free energy. Thank you for your patient listening.